Next bit we'll look at now is getting the equations from words and trying to work out the empirical formula. So in this 1.02 grams of copper was heated in oxygen, the black powder formed had a mass of 1.28 grams. Calculate the empirical formula of this oxide. So the first thing we do, write down exactly what's happening in words. We've got copper becomes an oxide because it was heated in oxygen. So copper plus oxygen gives me copper oxide. What we want to do at the end is work out this formula of copper oxide. Copper, being a transition metal, has a variable valency, so it's not always going to be CuO. It could be Cu2O, Cu3O, or such and such. We'll work it out from this. So 1.02 grams of copper, write in your information below it, was heated in oxygen. The black powder, which is copper oxide, had a mass of 1.28 grams. Now, with the law of conservation of mass, we were able to work out how much oxygen there was in it. So the final product had a mass of 1.28 grams. Copper contributed 1.02 grams of this. So this must mean the mass of oxygen is 1.28 minus 1.02, giving me 0.26 grams of oxygen. And just like the previous calculation, what we always go back to in chemistry, moles. So work out the number of moles of copper by dividing the mass by its mass number, 63.5, and work out the number of moles of oxygen by dividing the mass, 0.26 grams, divided by the mass number, 16. So 1.02, divide that by 63.5, 0.016 moles, and do the same there for the oxygen, 0.016. And you'll never write Cu 0.016 O 0.016. Trying to get that simple whole number ratio, divide by the smaller. Here we see they're both the same, so it works out pretty good. So the formula there is CuO, copper oxide. Next one, your magnesium. It was heated in oxygen and 1.2 grams of magnesium oxide was formed. Again, write down what's happening. Magnesium plus oxygen, giving me my magnesium oxide. How many grams of magnesium? I've got 0.72 grams. We don't know how much oxygen, but they told me how much product was formed, 1.2 grams. Therefore, to work out the mass of your oxygen, subtract the two figures, and we get there 0.48. 1.2 minus 0.72, 0.48 grams. What are we going to do with this? Go back to moles. So work out the number of moles of magnesium, dividing the mass by the mass number of magnesium, which is 24. Work out the number of moles of oxygen by dividing the mass, 0.48 grams, divided by the mass number, which is 16. So I'll work out the oxygen one first, since it's in me. Calculator 0.03 and 0.72 divided by 24, probably the same, 0.03 moles. Divide by the smaller one, again in this one, just so happens in the example they're both the same. So your formula there is MgO. Now, we'll do ones of decomposition then, and we'll get used ones to try there, 1 to 5 from the notes. And then we'll go over those then anytime you wish, but maybe in the live class. So 5.8 grams of an oxide of iron was heated. So this time we're starting off with iron oxide. We're heating it and we're getting the iron out at the end. So we're starting off with our iron oxide. We're heating it. We're forming iron and we're also forming our oxygen. It's an example of decomposition because we're breaking it down. Now fill in your masses. 5.8 grams of this. We form 4.2 grams of iron. How do I work out how much oxygen there is? Subtract these two figures and I get 1.6 grams. What do we always go back to? Go back to your moles and go back to the moles of the individual elements, iron and oxygen, because I don't know if it's Fe2O3, FeO, or whatever, you know, so you couldn't work out the relative molecular mass. Got to work with your individual elements. So number of moles of iron, 4.2 grams, divide that by 56, and your number of moles of oxygen, 1.6 grams, divide that by 16. So we're getting 1 over 10 for that one, or 0.1. And for this one, 4.2, divide that, 3 over 40, or 0.075. Not the nicest, but it's good that there's something different anyway. Divide by the smaller one then, which is your 0.075. We're getting 1 there. 0.1, divide that by answer. We get 4 over 3, or 1.33333. Again, we haven't got a whole number, but in order to get that whole number, multiply both of them by 3. Because if we times 4/3 by 3, we're going to end up with 4. And we times that by 3, we're going to end up with 3. So our formula there is Fe3, 3 irons, O4. Difficult wee one with the numbers. Pause it, maybe go over it, and you'll figure it out. And then the last one here, it's a hydrated substance. You've got hydrated sodium sulfate, 4 and 2 is 8. Was heated, it's found that 0.71 grams of the anhydrous salt. Anhydrous just means without water. You know, if you're hydrated, you've got water, and anhydrous without the water of the salt remains, so your sodium sulfate remained. Calculate formula of this hydrated salt. So we're starting off with your Na2SO4, and we're forming Na2SO4. We've got the formula of it, plus H2O. We just want to work out how many waters there are. So same again, fill in what information we've got. 1.61 grams of this. Our sodium sulfate, we don't need to work out the formula of it, but we're going to work out the number of moles of it. We've got 0.71 grams of our anhydrous salt, our sodium sulfate. To work out how much water there was that was driven off, subtract these two figures. We get 0.9. Now, work out the number of moles of these boys here. The reactants, if you wish, will come together to form that product. So your number of moles of your sodium sulfate, 0.71 grams, divided by the relative molecular mass of this, 2 by 23, 46, 1 by 32, 32, and 4 by 16, 64. Tally that up, 110, 142. And then divide by that. So 0.71 gives you 0.005 moles. Work out the number of moles of your water as well. So we've got 0.9 grams, divide that by 18, it's relative molecular mass. We get 0.05 moles. Divide by the smaller one, which is this. We get 1 and 10. Therefore, our formula is, it's told us how many waters there are. Na2, SO4, and 10 waters. Now, if you try there, stay down the bottom, questions 1 to 5. Have a wee look at your textbook as well. Have a way through them questions. Let's see, it's structural formulas, molecular formulas, page 162, questions 1 to 9. Batter on through those.